Let's wait for 2 more minutes because few more are joining. Then we'll start. Good evening, everyone. My name is Shubhranshu Purkasta, and I'm a PhD research scholar in the Department of Civil Engineering at IIT Kharagpur. I'm basically working as a Prime Minister Research Fellow at IIT Kharagpur under the supervision of Professor Mohammad Saud Afzal. My research area is computational fluid dynamics, uh, and I'm working on basically block body hydrodynamics. As you all might be aware that you guys have registered for this course on fluid mechanics in NPTEL, where the main course instructor is Professor Subhashisha Dutta from IIT Guwahati, and we have been assigned the task of taking a weekly 1 hour live session, where basically the main idea of this session is to discuss some basic problems, which will enable you to solve the assignment questions in a more better ways, in a more conceptual manner. So that is the main idea behind this exercise. So here you can ask your doubts even, but please don't, I mean, beforehand, before starting the session, it is very important to let you know that the assignment questions that are there, that you have to solve by yourself, because that is a part of your evaluation in this course. But of course you can clear your conceptual doubts, and here we'll try to take as like solve some conceptual problems which will help you in understanding the problems that are given in your assignment. So this is basically the week one of this particular session is based on the week one of your assignment, uh, fluid mechanics assignment. So in week one, whatever you have seen till now is that it's basically the fluid properties, and the most important component is you have you must have understood what is the basic difference between a solid and a fluid, and what is the constitutive equation, means how can you mathematically differentiate a solid from a fluid, and what is the physical basis of uh, that differentiation. So to begin with, as I told you, my name is Shubhranshu Purkasta, and all the lectures that will be taken during this live session will be available in this YouTube channel. The link I have provided, here, and might be from the NPTEL also. You'll be receiving the link. So you go to the channel, you visit the playlist CE85 Fluid Mechanics NPTEL, and there you'll be finding all these recorded versions of this live sessions. Now, uh, in order to conceptually understand this subject fluid mechanics, you need to follow some standard books. So you must have read one or more of these books that I've mentioned here. But the most fundamental book is Fluid Mechanics: Fundamentals and Applications by John Simbala and Eunice Sengel. It is a very good book, conceptually written, and the most intriguing part of this book is that it's written in a very simple language. It's written in a very simple language. Next, you can follow Fluid Mechanics by Frank White, which is slightly more complicated mathematically in terms of the concepts given in comparison to the Fluid Mechanics by Sengel and Simbala. So you can follow this book as well. Then, among our Indian authors, Fluid Mechanics and Fluid Machines by Professor Som Vishwas and Chakravarti is a very good book. And especially for boundary layer theory, you can follow the book of Fluid Mechanics by Monsoon Young and Okishi. So these are some books. There are many other books. So according to your convenience and whatever is available with you as per the resources available, you can follow any one of these books. But the important thing is you need to understand the concept. Now, as I told you, the week one of this course was dedicated to the basic understanding of a fluid, how a fluid is different from a solid, what are the constitutive equations, and what are the basic properties of a fluid. Now, uh, the can any one of you tell me what is the difference between a solid and a fluid from engineering point of view?
Uh, a fluid will be moving under action of a smallest shear stress indefinitely, but in case of solid, that will not be the case.
Yes, yes,
Yes,
yes,
hello,
yes.
sir.
Yeah.
If there is a constant shear force, then for a solid there will be fixed shear deformation.
Hmm.
But for that constant shear force, there will be continuous deformation in the fluid. So
Fluid
it is a property of continuum of fluid.
is the property of.
Is the property of continuum of the fluid.
Okay, continuum of the
Okay,
fluid.
continuum
Fine,
of the
fine.
fluid. Fine, fine. Yes.
So, if there is a elastic solid, if there is a elastic solid, then there is a very famous law which is known as Hooke's law of elasticity. So, can anybody tell me what is Hooke's law of elasticity?
Under elastic limits, under elastic limit, stress is directly proportional to strain.
Strain. Very good. Yes.
Very good. Yes.
So,
Sir, it is a limit of proportionality.
Hooke's. No, I'm just asking
No,
about
I'm just
Hooke's
asking
law.
about Hooke's law. Yes, sir. Stress is directly proportional to strain
Huh.
within limit of proportionality, not
Within elastic.
elastic limit. Elastic. Sir, within limit of
Limit of
proportionality.
proportionality.
Limit of
Okay, okay.
proportionality.
Got it.
Okay, okay.
Fine,
Yes. Got it.
fine.
Fine.
So, we have basically what you have told is that say stress sigma, it is directly proportional to strain within the limit of proportionality, and somebody told elastic limit. Fine, so that is Hooke's law of elasticity. Anyways, so what is the counterpart or analogous law that is available uh, for fluids? Which law?
Stress,
Huh? Yes.
Stress is
stress is
proportional to strain
directly
rate.
proportional to strain rate.
Strain rate. Okay. So can you tell me what is the reason? Means why there is a difference? Why there is a difference in the mathematical form of these physical implications or the constitutive law?
Because fluid never stops deforming and approaches towards constant rate of strain.
Okay. So yes, somebody was telling that fluids never.
Never stops deforming and approaches towards constant rate of strain.
Okay. So it approaches towards constant rate of strain. Yes. Fine. So the basic meaning is suppose you have say this is a block. Just mind my drawing because okay. Say which is fixed at the base. So say if it is a solid and if you deform this block, if you deform this block, say you apply some shear force F, then what will happen? It will deform. Now since its base is fixed, it will deform something like this. There will be a shear strain theta. Okay, there will be a shear strain theta. But the moment you release this force and if the solid body has not reached the plastic limit, okay, it will regain its original position, it will come back to its original position. But in case of a fluid, what happens? In case of a fluid, even if you remove this shear force, okay, or if you apply a shear stress, basically tau, it will not come back to its original position, rather it will keep on deforming. And as somebody told, this rate of deformation means d theta by dt, this rate of deformation will be constant. Okay, rather than a constant strain, the rate of deformation will be constant. So That's why we get tau is directly proportional to d theta by dt. Tau is directly proportional to d theta by dt. Now, uh, what is the implication of this? Okay, what is the implication of this? The implication of this is that what is this theta? Suppose you have, so this is a fluid element. So this is a fluid element which is fixed at the base, which is fixed at the base. Fluid element which is fixed at the base, and then you have applied some shear stress tau, because of which it has deformed. Okay, you have applied some shear stress tau. There is a deformation. So theta. Say the original length of this fluid element, this particular length was L, and say after deformation, the displacement from this original position to the deformed position is suppose delta L. Then what is the relationship between theta L and delta L for a small angular deformation theta? What will be the relationship between theta L and delta L?
Theta will be equal to del L upon L.
Theta will be equal to
Delta
Delta
L
L by
divided
L.
by L.
delta L by L. Okay, so how you are getting this?
Tan theta.
It
Because
is
theta is very
the
small.
it is the
Equal to
slope.
theta.
It is the slope between two layers of the fluid.
Yeah, you can basically interpret this from different angles, tan theta or the slope, or in a more fundamental way, what is the definition of an angle? What is the definition of an angle if you consider a circle?
Arc upon radius.
Yes, so you can use that. That is a more fundamental definition, or the definition that you have used. Uh, Say for tan theta or the slope that you told, that is also fine. So theta is delta L by L. Now, if theta is delta L by L, uh, okay, now what we want, we basically want d theta by dt. Okay, now just tell me one thing, d theta by dt and delta theta by delta t, are these two things same?
The difference is negligibly. It's infinitesimal if it's d theta. That's all.
No, means physically what is the difference between these two?
Physically, there's no difference.
uh, Physically there is no difference. Okay, fine. See, the basic idea is there is definitely a difference. D theta by dt. What does it means? That it simply means that it is the differential, right? So what is the meaning of this? The meaning is, what is the change in theta? What is the change in theta if there is an infinitesimally small change in t? Means with some change in t, what is the change in theta? But delta theta by delta t basically represents a ratio. Okay, it represents a ratio, but please mind this, many times we have seen that there is a little bit confusion here, uh, that this d theta by dt is treated as a ratio, but please remember that d theta by dt is not a ratio. Delta theta by delta t is of course a ratio, but this is not a ratio. It simply physically signifies that suppose you have two quantities dy by dx. Okay, so there are two quantities y and x, and y is dependent on x. So dy by dx physically signifies if there is a small change in x, what is the corresponding change in y. So uh, now these two things become equal if we consider this, as you told, as someone told just now, that if delta theta by delta t, there is no difference if this delta theta is very small. Yeah, that is fine. Okay, that is fine, because if you look from the graphical point of view, means if you draw a graph, and if the graph is having lots of curvature, means if it's a highly nonlinear graph, so if the difference, if the difference delta is very small, then those nonlinearities can be conveniently ignored. So with that assumption, okay, with that assumption that this theta is very small or this delta L is very small, because theta is delta L by L, what you can do is that we can find delta theta by delta t, okay, or d theta by dt. So what will be this? So this will be particularly d dt of, sorry, so this will be d So dt of delta L by L. Okay. Now, if you look at this, L is basically a fixed, it is basically a fixed length. Okay. So this will come out of your derivative. And what is d dt of any length dimension? D dt of any length dimension is basically velocity. Now in differential form, that's how you are getting that tau is directly proportional to du by dy. Okay, in differential form, that is basically a velocity and some length. Okay, in differential form. So that is the physical as well as the mathematical basis of Newton's law of viscosity, and it is basically the constitutive equation for fluids. Okay, so for viscous fluids. Okay, Newton's law of viscosity is basically the constitutive equation for viscous fluids. So the weak one, uh, leaving aside the very fundamental fluid properties like density, specific gravity, or maybe surface tension, a very important thing, the very fundamental thing associated with the fluids is the Newton's law of viscosity. Okay, so we'll look at few problems, very basic problems. uh, However, you need to remember that you should, though the problems, okay, the problems may appear very simple, but you should have a good grip, because in some advanced chapters, for example, in boundary layer theory, or in turbulent flows, or in the exact solutions of Navier-Stokes equation in some simplified cases, you need to have a very good understanding of this Newton's law of viscosity. So let us look at the first problem. So the first problem, it's a very simple problem. The Just excuse me. Okay. The space between two parallel plates kept 3 millimeter apart is filled with an oil of dynamic viscosity 0.2 Pascal second. What is the shear stress on the lower fixed plate if the upper one is moved with a velocity of 1.5 meter per second? So this is basically a situation, okay, the diagrammatic representation of the problem. So there are two plates, upper plate and the lower plate, which are separated by a distance of 3 millimeter. Okay. The lower plate is kept fixed, whereas the upper plate moves towards the right. Okay, the upper plate moves towards the right with a velocity of 1.5 meter per second. Okay. Now, in between these two plates, there is some lubricant, that is basically a oil, having a dynamic viscosity of 0.2 Pascal second. Okay, and you need to find what is the shear stress on the lower fixed plate. Okay, now here it is a direct application of Newton's law of viscosity. So Newton's law of viscosity in its full form, okay, in for 1D flow is uh, not basically 1D, you can consider it for 2D. Basically, the velocity gradient will be along the y direction. Okay, the gradient is along y direction, the flow is taking place along x direction. So when I told one dimensional, it basically means that the flow is predominantly along the x direction. There is no flow taking place along y direction. The flow is basically taking place along x direction, but the gradient is along y direction. So for that particular form, the Newton's law of viscosity can be written as tau is equal to mu du by dy, where mu is the coefficient of dynamic viscosity. Okay. Now, du by dy. If we consider that this gap is very small, that is 3 mm, is very small, then this du by dy can be approximated as a ratio, as someone told some time back. So this is basically say level 2 and this is say level 1. Okay, say the lower plate is level 1 and the upper plate is level 2. So u2 minus u1 divided by y2 minus y1. So what is u2? Since the upper plate is moving towards right with a velocity of 1.5 meter per second, and you can consider the positive x-axis, okay, is having a positive velocity. So put 1.5, and the lower plate is stationary, so it is 0. Similarly, y2, okay, y2 minus y1. So if you consider that the origin lies on the lower plate, okay, if the origin lies on the lower plate, then uh, y1 is 0 and y2, that is the upper plate, the y coordinate will be 3 mm. So 3 into 10 to the power minus 3, that is mm being converted to meter. So du by dy is 500 per second. Now the shear stress, basically by using this Newton's law of viscosity is mu, which is 0.2 Pascal second. So it is directly given in SI units. So there is no need to convert. And du by dy is 500 per second. So it is basically 100 Newton per meter square. So it is a very simple application of Newton's law of viscosity. So I hope this problem is clear, and you must have solved this type of problem many times before. Then another problem means, this is just an example, a generic example. Sometimes in some competitive exam, maybe in GATE or in engineering services, rather than giving a statement like this in the earlier problem that we have seen, you might be given a velocity profile. Okay, the velocity distribution in a viscous flow over a plate is given by u equal to 4y minus y square, when you have to keep this thing in mind that y is less than 2 meter. Okay, and here u is the velocity in meter per second at a point distant y from the plate. Means there is a plate. Okay, there is a plate, there is a plate, there is some fluid that is flowing over this plate. Okay, and the velocity, okay, the velocity profile is 4y minus y square. So it is basically a parabolic profile. So the velocity profile is given to you. So some parabolic profile, the distribution is given to you. It is basically 4y minus y square. But you have to keep in mind that one constraint is given, that y is less than equal to 2 meter. Okay, means this expression is valid, this velocity profile is valid when y is less than equal to 2 meter. So normally the the origin lies on the plate. Okay, and from the plate it is given in the question that u is the velocity at a point distant y from the plate. Okay, so if you consider any point, say point P, okay, which is at a distance y from the plate, so at that point P the velocity profile or is given by 4y minus y square. Okay, means the velocity at that point is whatever is the y coordinate here, 4y minus y square. But this expression is valid till y is less than 2 meter. So the question is, what happens if y is more than 2 meter? If y is more than 2 meter, then this gradient that is formed, okay, means this velocity, okay, this velocity and the free stream velocity are basically the same. Okay, that is one scenario. Or another scenario is the total thickness of the flow, means the depth of the flow of that particular fluid is 2 meters. So that's why it is valid. So there are two possible cases. One is if there is a boundary layer formation, then at this particular, means at y equal to 2 meter, this particular value of velocity matches the free stream velocity. Or the second scenario is the total depth of flow, or the depth of the whatever fluid is flowing over the plate, the depth of flow is 2 meters. So you have to keep this condition in mind. Then if the coefficient of dynamic viscosity
Sir, the
is,
screen is not visible.
screen
The
is not
screen is
visible,
not. Yes.
No, it's visible.
it's visible for others, right?
Visible, sir.
Sir, visual, sir.
Clearly visible.
Okay, okay. So
Yes, sir.
okay, fine. So I don't know who said it is not visible. You please check your settings. Okay, you please check your settings. Okay. Fine. So if the coefficient of dynamic viscosity is 1.5 Pascal second, you have to determine the shear stress at y equal to 0 and at y equal to 2 meter. So y equal to 0 is basically y equal to 0 is basically the plate. Okay, on the plate, what is the shear stress on the plate? And at y equal to 2 meter is basically the location or the point till where this velocity profile is basically valid. Okay, now before going to the solution, let us discuss important aspect of Newton's law of viscosity. Sorry. Say this is a fixed plate. Okay, say this is a fixed plate, and there is some particular velocity profile on this plate. Okay, so there is some particular velocity profile on this plate. Now, according to Newton's law of viscosity, tau is directly proportional to du by dy. Okay, tau is directly proportional to du by dy. So my first question is, where is the shear stress maximum? Okay, and you suppose that your origin lies on the plate. Okay, so where is the maximum shear stress? Where do we expect maximum shear stress and why?
To the plate, sir.
Okay, why?
Because the slope is maximum on the at that curve near the plate.
Slope is maximum at, very good. Yes,
Maximum.
maximum. Yes, on the plate. Yes. So,
Yes.
yes, good. So, whatever he told is very much correct. You look, shear stress is basically directly proportional to du by dy. So du by dy is basically, if this is the y direction, if this is the y direction, then du by dy represents the slope of the velocity, okay, along this y direction. Now, if you look at this curve, okay, the slope means with a small change in y, what is the corresponding change in u? Okay, so this particular slope is maximum here. Okay, now here the velocity is zero because of the no slip boundary condition. Okay, here the velocity is zero, but the velocity gradient is maximum. Though the velocity is zero, the velocity gradient is maximum in this location, okay, on the plate surface. Okay, there might be some confusion that since velocity is 0, du by dy is 0. No, the velocity is 0, but the velocity gradient is maximum, and as a result of which we get maximum shear stress on the plate surface. And as you keep on moving away from the plate, the value of the shear stress decreases. Okay, so you will get a better picture here. So in this particular problem, you can see that in this particular problem, you can see it as u is equal to 4y minus y square. Okay, this is the velocity profile. Hence, the velocity gradient will be 4 minus 2y. Okay, and if you use this particular expression of velocity gradient in the Newton's law of viscosity, then tau is equal to mu 4 minus 2y. So 4 minus 2y is basically du by dy. Now you have to obtain the shear stress at y equal to 0 and y equal to 2 meter. So at y equal to 0, that is on the plate, tau is 1.5 times of 4, that is 6 Newton per meter square. Okay, and at y equal to 2 meters, you can see that 4 minus 2 into 2, so this is basically 0. So where is you are obtaining the maximum shear stress? Maximum shear stress is obtained at y equal to 0, that is on the plate surface. So that is this is a very important concept, you please remember. And again, this concept is very much useful when you will be learning about the boundary layer flow. Next, going a little further, there is another problem. In 90 Newton solid rectangular block, there is a solid rectangular blocks which slides down a 30-degree. There is an inclined plane. Okay, there is an inclined plane which is making an angle of 30-degree with the horizontal. Okay, now the plane is lubricated by a 3 mm thick film of oil. Okay, so here you can see that this particular plane is lubricated by making use of oil. Okay, whose relative density is 0.9 and whose viscosity is 8 poise. Now, if the contact area between this block and this inclined surface, okay, if the contact area between this block and the inclined surface is 0.3 meter square, you have to estimate the terminal velocity of the block. Okay, so please read the question carefully. A 90 Newton solid rectangular block slides down a 30-degree inclined plane. The plane is lubricated by a 3 mm thick film of oil of relative density 0.9 and viscosity 8 poise. If the contact area is 0.3 meter square, you have to estimate the terminal velocity of the block. So please don't look at the solution. Read the question carefully and please let me know if the question is clear or not. What is being asked from you, is it clear or not? So I hope the question is clear. Now, what you have to estimate? You have to estimate the terminal velocity. So, can you tell me what you have understood or what you have interpreted from this term terminal velocity?
Sir, when
From this point
the
onwards, the velocity won't change.
Yes, the velocity won't change, or basically, uh, the net acceleration will be not there. Okay, it will be coming down with a constant or uniform velocity. So that is the terminal velocity. Now, for in order for that body or for the rectangular block to attain terminal velocity, what is the condition? The condition is along this direction, the direction along which it is sliding down, along this particular direction or the direction of its motion, the net force acting on this block should be equal to 0. The net force acting along the direction of the motion of this block should be equal to 0. So, what are the forces acting on this body? Okay, so there is the weight which is acting the downward direction. Now, since it is sliding along this inclined plane, there will be a shear stress. Okay, there will be a shear stress acting in the opposite direction. Okay, and this is the velocity. Okay, so this v basically represents the terminal velocity. So if you look at this, okay, so what are the forces that are acting? So along this direction, along the direction of the motion, there will be a component of weight. Okay, there will be a component of weight. And what is that component? It is w sine theta. Okay, and opposite to this direction there will be tau, means tau is shear stress. So when you multiply area with stress, you get force. So which area you will multiply? It is the contact area. Okay, so the contact area is the area of contact between this block and the inclined plane, and in between which what is there? There is a fluid. Okay, or there is a oil. Okay, a lubricating oil is there, so which is acting along the opposite direction. So if you write uh, by following proper sign convention, so w sine theta, so you take the force acting along the direction of motion of the block as positive, so that is w sine theta. So you can simply write and what is the force that is acting in the opposite direction? That is minus tau a. So this should be equal to 0. So from this expression, what you can get, tau is equal to w sine theta by a. So that is our equation 1. Tau is equal to w sine theta by a. That is our equation 1. So is it clear till this point? Okay, fine.
Yes, sir.
Okay. Fine. Now, from Newton's law of viscosity, we know that tau is equal to mu du by dy. Okay, tau is equal to mu du by dy. So this mu du by dy, if you look at this figure carefully, okay, so it has attained terminal velocity, and this terminal velocity is basically a constant velocity. Yeah, Tech Deva, please mute yourself. Okay, so mu du by dy. Now, if you look at this, okay, what is the thickness of this lubricating fluid layer? It is 3 mm. Okay, so you just consider this inclined view. So this is one surface, this is another surface. So the velocity on this surface is v, and the inclined plane is fixed. Okay, and since this block is moving downwards with a velocity v which is constant, okay, this particular upper fluid layer, okay, this particular upper fluid layer will basically mimic this particular velocity v. Okay, so basically du by dy, so du is u2 minus u1. So what is u2? U2 is v, u1, that is basically the top surface of this inclined plane, which is 0. So sorry, v minus 0 is basically v. And what is this h? H is nothing but the thickness of this layer. Okay, So h2 minus h1 or y2 minus y1, y1 is 0 if you look at the coordinates, and this total thickness will be 3 mm. So tau is equal to mu v by h, which is equation 2. Now if you look, tau is equal to w sine theta by a is equation 1, and from Newton's law of viscosity, tau is equal to mu v by h, which is our equation 2. So if you equate 1 and 2, mu v by h is equal to w sine theta by a. So from this you can get the value of v, which is terminal velocity, hw sine theta by mu a. So the value of h is 3 mm, so 3 into 10 to the power minus 3 meter. W is basically the weight of the block, which is 90 Newton. The value of theta is 30 degree as given in the question, sine 30 degree. Mu, okay. Now here, sometimes in some problems you might see that the value of the viscosity is given in SI unit. So what is the SI unit of dynamic viscosity, coefficient of dynamic viscosity? It is Pascal second.
Pascal second.
Yeah, and what is the SI unit of kinematic viscosity?
Meter square per
Meter
second.
square per second. Meter square per second. Yes. So in this particular problem, the viscosity is given as 8 poise. So what is it? What is the meaning of this 8 poise? What does it represent? Dynamic viscosity or kinematic viscosity?
Dynamic
Dynamic.
viscosity.
Dynamic.
Dynamic viscosity.
Yes.
Okay, and if you have to convert poise to Pascal second, what is the conversion factor? The conversion factor?
Divided by 10.
0.0.
Divide by 10.
Divide by 10.
Yeah, divided by 10. Yeah, divided by 10. Or multiply with 0.1. So 8 into 0.1, and the contact area is 0.3 meter square. So basically you will be obtaining after the calculation a value of 0.5625 meter per second as the terminal velocity. So I hope this problem is clear. Next
Yes, sir.
problem. Yeah. Next problem. There is a table given to you. Okay. So classify the fluids A to E. So A, B, C, D, E. There are 5 fluids based upon the following results of a test on their rheological behavior. Okay. So some tests were performed on the fluid, okay, to determine their rheological behavior or the flow behavior, okay, and whatever values are obtained. So this upper row represent the shear rate and the lower row represent the shear stress tau. So there are 5 fluids A, B, C, D, E, and for each of the fluids, shear stress tau and the correspond shear rate, delta U by del Y and shear stress tau corresponding values are given, okay, in some particular standard units, okay, in some values in units. So what is the meaning of these values in units? Means whatever units they are given in, they are basically compatible, okay. If suppose these values are in SI, then all the values are in SI. If say if these are in CGS, then all the values are in CGS. So you don't have to worry about the units, they are in compatible units, okay. Now for fluid A, you can see that at when the shear stress is 0, shear rate is, or the shear rate of shear strain is 0, and then you get some other values when the shear stress is more than 0. For fluid B, the shear stress when it is 1 unit, the shear strain is 0, okay, and for all the other cases, uh, corresponding to a 0 value of shear stress, the shear strain rate is 0. So the best way to solve this kind of question is to prepare some rough graph, okay. So this is the graph, okay, this is the graph. So fluid A, for fluid A you can see that shear stress is 0, shear rate is 0. Then when shear stress is 1, shear rate is rate of shear strain is 0.5, okay, for fluid A 1, 0.5. So if you draw the graphs, okay, if you draw the graphs, you can see that there is a linear increase, okay, there is a linear increase. So if there is a linear increase, then what is this? Basically it is a Newtonian fluid, okay. For fluid B is interesting because when the shear stress tau is equal to 1, the shear strain is 0. So this is our fluid B, okay, fluid B. But otherwise all the value, means all the plots lies along a straight line. So What is this type of fluid known as? This is known as a Bingham plastic. Next, you look at fluid C. So, if you plot the corresponding values in case of fluid C, what you are getting? This is basically fluid C. Okay, what you are getting? It shows that shear stress decreases with the increase of shear strain rate. Okay, you look here. The shear stress decreases. Okay, the shear stress decreases with the increase in shear rate. So non-Newtonian fluid, and it is pseudoplastic. So simply by looking at the variation of these graphs, you can determine what is the type of fluid. Now fluid E here is quite interesting because you can see that whatever is the value of shear strain rate, the value of shear stress tau is always zero. The value of shear stress tau is always zero, whatever is the value of shear strain rate. So what is this? This basically is a point. Okay, so fluid E is basically a case of ideal fluid. So what exactly is the ideal fluid? Can anyone tell me what is an ideal fluid?
When there is no viscosity and equilibrium fluids.
Yes, yes. So basically, an ideal fluid is one which is having zero viscosity or inviscid. Okay, so this is one type of problem. You can do this problem, like you can solve this type of problem. You can draw the graph. You can if you have say the resource, then you can draw this graph in the Excel, and then you can see the behavior and you can determine the type of fluid. Okay, then let's move to the next problem. Next problem is, what change in pressure is required to compress a gas under isothermal conditions to quarter of its original volume. Okay, so what pressure is required to compress a gas? Means there is a gas. As we know that both gases and liquids are fluid. So if there is a gas under isothermal condition, what is the meaning of isothermal condition?
Constant temperature.
Yeah, when for a system the temperature is not changing or the temperature is constant, it is known as the isothermal condition. So under isothermal condition, how much change in pressure is required to compress a gas? Okay, but what from to quarter of its original volume, means suppose if the original volume is V, then how much pressure is required to change the volume to V by 4 or 1/4 of the V. Okay, so if V is the original volume, then what is the change in volume? V2 minus V1. What is V2? The new volume that we desire is 1/4 of the original volume V minus V. Okay, so the resulting value is minus 3/4 of V. Now what is, from the definition of bulk modulus of elasticity of a fluid? Okay, so which is what denoted by K here. So K is basically dP by minus of dV by V. Okay, now why this negative sign? This negative sign basically implies that when you apply pressure from the outside, what happens? When you
Volume will be reduced.
volume will be reduced. Okay, so when you apply pressure from the outside, volume will be reduced. So that is the significance of the negative sign. So dP, so from the definition, dP is equal to, that is the change in pressure, is equal to minus of dV by V into K. Now for isothermal conditions, now it is basically a very standard observation of physics. Okay, at isothermal conditions, K is equal to P, that is the bulk modulus of elasticity is equal to the pressure, original pressure. Hence change in pressure, if we use this formula, C minus of dV by V, so what is delta V? Minus of 3/4 of V, okay, divided by V, and what is the value of K? P. Okay, so where P is the initial pressure of the gas. So what is the change in pressure? Change in pressure means you have to apply 3/4 of the original pressure. Okay, means that is the change. So with the original pressure, if you apply 3/4 of P, means that additional pressure, then the volume will reduce to 1/4 of the original volume. So that is the significance of this problem. So here one important thing, particularly for civil engineering students, please be careful that we often neglect the importance of the gas laws. or the conditions, the thermal conditions like the isothermal conditions or adiabatic conditions. So please be careful while studying this chapter or this portion on bulk modulus of elasticity or coefficient of compressibility. You need to have a fair idea on the different state equations which define the state of a fluid. Okay. Next, a liquid with a specific gravity of 0.87 undergoes a reduction in volume of 0.11% when subjected to an increase in pressure of 1500 kilopascal. And then we have to estimate the velocity of propagation of sound in that particular liquid. Okay, please understand the question carefully. A liquid with a specific gravity of 0.87, okay, undergoes a reduction in volume of 0.11% when subjected to an increase in pressure. Okay, means there was some original pressure P, and when that pressure is increased to 1500 kilopascal, okay, it the liquid, there is a reduction in the volume of the liquid by 0.11%, okay, from its original volume. So we have to estimate the velocity with which the sound propagates or sound travels in that particular liquid medium. Okay, so here what are the details given in this question? Sorry. So what is the volumetric strain? Delta V by V, negative, because the volume has reduced, so that's why the negative sign. 0.11% or 0.11 divided by 100, so 0.0011. Okay, then what is the value of delta P? That is the increase in pressure or the change in pressure. It is 1500 kilopascal. Okay, then excuse me, then if you again use the definition of the bulk modulus of elasticity of the fluid minus delta P by del V by V. Okay, now 1500, but you have to remember that this 1500 is in kilopascal, so you need to make suitable changes in the units. So whenever there is kilopascal, you need to multiply with 10 to the power how much?
3.
3. 10 to the power 3 for making it pascal, that is SI unit. And since this is volumetric strain, there is no unit for strain. So with this you will be getting the value of bulk modulus of elasticity, which is 1.364 into 10 to the power 9 pascal. Now what is the velocity of sound? Okay, what is the velocity of sound in the liquid medium? It is square root of k by rho. So k is, you have already calculated k, which is 1.364 into 10 to the power 9 pascal, and rho basically is density. Now how will you obtain density? In this question, the specific gravity of the liquid is given to you. So what is specific gravity?
Density of liquid given by density of water.
Density of water. So it's basically, specific gravity is a number, okay, which signifies how dense is a particular liquid relative to water. Okay, so here 998 kg per meter cube, or the standard value. See, if nothing is given in the question, you can always use the value of 1000 kg per meter cube as the density of water, or 998. But please look at the questions carefully. Sometimes in some competitive exams, in the question, the value of the density is given. Okay, and it is given in order to create confusion, because we have a habit of, whenever we look at density of water, we immediately put 1000 or 998 or maybe 999, something like that. But sometimes in some particular problems the value of the density is provided, so please look at the data carefully. So 0.87 multiplied with the density of water basically gives the velocity of sound in that medium. Now let me go back to a particular question. Now, this question that we have already solved, we have already seen the problem of is a block sliding along an inclined plane. Here, in this particular equation, you can see that we have used this value 90 Newton for in calculating the final answer. We have used this value of 30-degree inclination. We have used this thickness value of 3 mm. We have used the viscosity of 8 poise. We have used the value of the contact area of zero point 0.3 meter square. But there was one additional detail, relative density of 0.9. Now sometimes in some problems, some additional parameters might be given to you just to confuse you. Okay. But as you have seen in this question, there was no role of this particular value of 0.9. Okay, relative density of 0.9, it was not used. Okay. Now, if I ask you, suppose you have to make use of this relative density in this question, what changes you will make in this particular question? What changes you will make? If suppose you want to use the value of this relative density of 0.9.
So can you please repeat the question?
Yeah, see, in this particular question, we have already seen, right? This particular question. There, in this particular question, we have not made use of this particular parameter, that is the relative density or specific gravity of the lubricating fluid, which was there. 0.9. We have not made use of this particular parameter, that is relative density. But suppose you want to make use of relative density in this question, then what
Sir, instead of
yes, instead of,
if kinematic viscosity was given instead of dynamic viscosity,
yes, in this particular
then we
question,
could have made.
yes, good, thank you. So in this question, relative density value was not used because the viscosity value that was supplied to you was already the coefficient of dynamic viscosity. But suppose uh, rather than the coefficient of dynamic viscosity, you were provided with the value of coefficient of kinematic viscosity. So in that case, in order to obtain coefficient of dynamic viscosity from the coefficient of kinematic viscosity, you would require the value of the density, and there you could have made use of this relative density. But since in this question it is already given 8 poise, that is the unit of dynamic viscosity, this thing was not used. So whatever parameters are given to you, please go through the units very carefully, and especially in some problems intentionally the units are given in some systems other than SI unit, just to confuse the candidates. So you need to be very careful. Okay, what are the values supplied to you, what are the units, and what are the values that you need to make use of, and then you do the calculations. Now just at the end, this is a question. uh, Glycerin has a density of 1260 kg per meter cube, and it has a kinematic viscosity of 0.00183 meter square per second. Okay, the question is, what shear stress is required to deform this fluid at a strain rate of 10 to the power 4 per second? Okay, so how will you solve this question? You can see that in this particular problem, what are the given values? Kinematic viscosity, that is nu, is given to you 0.00183 meter square per second. The value of the rate of shear strain or the velocity gradient is given to you. What is the value of the rate of shear strain? The value of the rate of shear strain is 10 to the power 4 per second. The value of density is given to you 1260 kg per meter cube. Okay. Now, what you need to obtain? You need to find, finally, what is your objective? Your objective is to find the value of tau, that is shear stress. Now, we have to make use of Newton's law of viscosity. Tau is equal to mu du by dy. And
2.3 into 10 to the power 4.
yes, see, I have not calculated the answer, but you have got it right.
Yes,
So
sir.
yeah, so you have to obtain mu from mu, that is coefficient of kinematic viscosity, and rho. Okay, you have to obtain mu from mu and rho, and once you know the value of mu, once you have the value of mu, you can very easily find the value of tau from the Newton's first law of viscosity. So that's all for today. Thank you very much. We will again meet the same time next Tuesday with our week 2 solutions. It's already time.
Okay, sir. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.